अच्छा अच्छा ठीक ठीक है ठीक है. Now, see here, in the previous class we have discussed the various cases for the sandy soil. The first and the simple case was there is a dry cohesionless backfield. Where there is a dry cohesionless backfield, the water table, there is no water table. In that case, the pressure is increases with the depth, zero pressure at the top and maximum at the bottom. Right? Then there is another case where the soil is in a completely submerged condition. When the soil is in a completely submerged condition, over the wall there are two types of pressures which are acting. One is due to the submerged soil bed, and another is due to the water table, right? So that is the second one. Then the third case where there is a surcharge, then there is a layered backfill. That we will that all cases we have discussed in the previous class. Now we'll come to the numericals, right? So in this case, we will just consider this is the retaining wall. This retaining wall of height h and h is equal to 6 meter, and it contains the same backfill but water table is at a 2 meter depth, right? So the complete wall is of 6 meter, where at 2 meter depth there is a water table, and therefore the 4 meter that will be considered as h2, which will be in a submerged condition because the water table is over here. So this soil becomes in a completely submerged condition, right? The properties are given. The properties of the soil are given as phi is taken as 30°, that is angle of shearing resistance is taken as 30°. Density is taken as 18 kN per meter. Now, this portion of the soil mass becomes a submerged condition. Therefore, we have to consider the gamma submerged. Now, what is gamma submerged? Gamma submerged is equal to gamma saturated minus gamma W. But in this problem, the submerged unit weight is already given in the numerical, so we will just take the whatever given in the numerical. Now first we will just calculate Ka, that is the coefficient of active earth pressure, and that is equal to 1 minus sin phi upon 1 plus sin phi. So as the phi is given as 30°, therefore Ka is found to be 0.33, right? Now in this case, there are two layers of the soil. There are two layers of the soil. So this is first layer and this is the second layer. So first layer is a dry cohesionless backfill, dry sand, and the bottom layer we just consider this first layer is dry sand and the second layer is submerged sand. Submerged sand. So we will just assume the first layer. That first layer is considered to be the dry cohesionless soil, and here the distribution is a triangular distribution where the pressure at the top is 0, because in the sandy soil the pressure at the top is 0 and increases with the depth, as sandy soil has a tendency to just put their weight over the adjacent structure. An adjacent structure in this case is a retaining wall. So soil has a tendency, sandy soil has a tendency to just give all its mass to the adjacent structure. Therefore, it's starting immediately the pressure from the top itself. But over here, it will be 0 and maximum at the bottom. What will be the intensity at the bottom? It will be Ka into gamma into H1. In this case, it will be H1. So this is the pressure at the top, where I will consider this is pressure distribution diagram 1. Now, here the self-weight of this soil act as a uniformly distributed surcharge load, and which will be acting over the bottom load, right? So here this self-weight of the soil is act as a surcharge weight over the second layer, and therefore we will just take this as a surcharge load, and here this is the intensity which will be acting at the interface of the first and second layer. So over the top of the second layer, this surcharge will be acting, and the intensity of the surcharge is equal to Q is equal to gamma 1 into H1. So what will be the gamma? It will be 80 and the height is 2 meters, so it will be a 36 kilonewton per meter square. Right? So these uniformly distributed loads having the same intensity over here, and therefore it will be uniformly acting throughout the depth. And these surcharge we have placed over here, so this part of the wall will carry the load of the surcharge and which will be same throughout the depth. It will be same over here, and same over here. Therefore, the distribution diagram is rectangular, right? And the intensity is again same. It will be this intensity. This is Q and this is K. So it will be Q into Ka and the same intensity, that will be 36, right? Then there is a second weight on this portion of wall. Another weight is due to the submerged soil weight and another is due to the water pressure. So here we'll just draw the another diagram, second diagram. So that will be the first distribution or the first self weight, that is due to Ka into gamma submerged into H2. Here it will be Ka into gamma submerged into H2. Then the another pressure is due to the water. So it will be intensity is gamma W into H2. So the first pressure is due to the submerged weight, that is Ka into gamma dash into H2, and another pressure that is due to the water. Now there are three distributions diagram. This is distribution diagram 1, this is 2, and this is 3. Right? So again we will calculate the area of all the three distribution diagrams. Here, what is then A1? A1 is half of Ka into gamma into H1 into H. Then what is A2? A2 is again a rectangular distribution diagram. Therefore, the rectangle area we will take into consideration, and that will be Ka into gamma into H1 into H1. Then the third is A3, which is again a triangular distribution diagram. So as it is a triangular distribution diagram, again what is the area of the triangular distribution diagram? It will be Ka into gamma submerged into H2 plus gamma W into H2 into H2. Why we are taking it as H2? Because H2 is the layer, that is the height of the second layer, and we are calculating it for a particular second layer, therefore H2 will be taken into consideration. So what is total PA in this case? PA is the A1 plus A2 plus A2. Now this combined pressure distribution diagram, that is combined PA, will be at Z bar distance from the water. Now in this case, what is A1? A1 is found to be, it is found to be 12. This A1 is found to be 12. As this is 36, and here it will be 2. It is found to be 12. Then the another, that is again found to be this is 12 actually. This is not 36. Again it multiplied by 0.33. So it is found to be 12 over here. Same 12 over here. Same 12 over here. And this total will be act as 39.24. So these are the answers. In this case, the first PA1 is found to be 12, another is found to be 12, and the last one is 102, 102.4. So what is total PA? Total PA is obtained as 164.48 kilonewton per meter run. So this is total PA. Now, where it will be at, this total PA will be at some distance from the bottom, and that some distance is calculated as a Z1. Now, here this is first PA or first A1. A1 is acting at how much distance from the bottom? It will be H2 plus H1 by 3. It will be H2 plus H1 by 3, and this is found to be Z1. So this is Z1. Right? So we will be just calculate Z bar is equal to 4 plus 2 by 3. It will be 164.48 kilometer per meter. Right? So this is Z1. Then another is the distance at Z2. So this Z2 is 4 by 2, which is outlined to be 2, and Z3 is equal to H2 by 3. So what is H1? H1 is, Z1 is equal to H1 plus H2 plus H1 by 3. Then Z2 is, as it is a CG of the rectangle. This is the rectangular diagram where the CG of the rectangle will be at, it will be at H2 by 2. And third, H3 is equal to H2 by 3. Now, where the combined CG will be at? It will be at PA is equal to A1Z1 plus A2Z2 plus A3Z2 and divided by total P. So here, this Z bar is found to be 1.75. This Z bar is found to be 1.75 meter from the bottom. So this is the first numerical, which is a very simple type of numerical. I think you must have cleared this numerical. We will now switch to the second type of numerical. Okay. Then the second numerical, again here we are considering a retaining wall of 6 meter height and retains two cohesionless backfill where the upper 3 meter and the lower 3 meters are the different soil layers. In the previous numerical, what we have discussed, there is a single layer, means the soil throughout the backfill is a homogeneous backfill, but it is partially submerged. Upper one, in the upper layer, the soil is in a dry condition, whereas in the lower one, the soil is getting submerged. But the soil layer was same throughout. But now in this numerical, we will discuss there are two layers. So again, here, this H is equal to 6 meters. Then there are two layers. So first H1 is 3 meter and H2 is 3 meters. Right? Then the gamma 1 is 18. Gamma 1 is 18. Phi 1 is 30. Then there is a second layer where gamma 2 is 20 and phi 2 is 26. But in this case, the soil layer is of the same type, is of different type. So in this case, I just draw a pressure distribution diagram first. Prior to that, I just calculate the value of Ka1, which will be 1 minus sine of 30 divided by 1 plus sine of 30. So it is found to be 0.33. Then Ka2 is 1 minus sine 26 upon 1 plus sine 26. So it is found to be some value, right? Abhi, this is the first layer where there is a dry cohesionless backfill is considered. Now in this case, both the layers are a dry cohesionless backfill. So first, it is a simple case where there is a dry cohesionless backfill. And what is the bottom ordinate? It will be Ka1 into gamma 1 into H1. So here this is the pressure distribution diagram for the first layer. Now the second layer is we will consider as a separate layer, and this portion of the soil is converted into an equivalent surcharge load, and that will be acting over the interface of first and second layer. So here this will be act over the face, and therefore this will be Q, which is gamma 1 into H1. So what is gamma? It is 18. So it will be 54. This will be act as 54 kilonewton per meter square, which will be acting as a surcharge. Now, if there is a surcharge load, this surcharge will be uniformly distributing over the whole portion of the retaining wall, and it will be throughout same. Therefore, the pressure distribution due to this will be same. Now, what is the difference between this case and the previous case? Here, the same we have taken into the bottom one because soil layer was same. But in this case, here we will consider Ka2 into Q. It will be Ka2, whereas in the previous numerical we have considered Ka1 as the soil was homogeneous core. Only there is a water table, due to that there are layered soil as considered. So here this is Qa2 into K2. Then again there is a same diagram for the dry cohesionless backfill, and here this is the diagram for dry cohesionless backfill. It will be Ka2 into gamma 2 into H2. So these are the three diagrams that we will obtain. This is diagram number 1, this is diagram number 2, this is diagram number 3. Right? So in this case, what is the intensity? It is found to be 18 over here. Ka1 into gamma 1 into H1 is found to be 18. Then Ka2 into K2 is found out to be 21.06. And the last it will be 23.04. So these are the bottom values. Now, where the Z will be at which distance this Z will be at. So here we will consider this is P or A1. The A1 is at Z1 distance, so it will be H2 plus H1 by 3. What is H2? H2 is 3 meter and 3 by 3 is 1 meter, so it will be 4 meters. Then there is another one, that is A2, area of the second pressure distribution diagram. Here it will be at Z by 2, Z2 distance, and this Z2 is 3 by 2. It will be H2 by 2, and here it is 1.5 meters. Then here it will be at a 1/3 distance from the bottom, so it will be Z3, which is H2 by 3, and it is found to be 1. Right? So these are the three pressure distribution diagrams that we have obtained. So we will just first calculate the area of the first distribution diagram, and that is found to be the total distribution PA1 is half of 18 into 3. So it will be 27. Then PA2, or we will consider A1. Then A2 is 21.06 multiplied by 3 meters. It is found to be 63.18. Then A3 is, again there is a triangular distribution, so it will be half of base is 23.04 multiplied by 3. So it is found to be 351, sorry 35.1, right? So in this case, we will just assume what is their total PA? Total PA is equal to 125.28 kilonewton per meter run, and Z bar is equal to A1 into Z1, so it will be 27 multiplied by 4 plus 63.18 multiplied by 1.5 plus 35.1 multiplied by 1. So it is Z bar is found to be 1.9 meters from the base. Right? So it will be this distance. Now, this is about the second case where there are the two layered swirls. Right? Now we will discuss the third type of numerical where we are considering the surcharge swirl. Right? In this case, we will consider a retaining wall third case, determine the active work pressure for the retaining wall 6 meter high, right? So here again we will consider a certain wall which is considered at a depth of h is equal to 6 meters, h is equal to 6 meters. Then it retains a dry homogeneous battery of gamma is 18 kilonewton per meter cube. Then phi is again assumed as 30 degree. And here you have to determine the pressures without any surcharge and with surcharge. Now in this case, this is the simple case of a retaining wall. You have to find out the pressure when there is a surcharge weight of 24 is placed over here. So it will be Q is equal to 24 kilonewton per meter square is the surcharge which is acting over the top of the backfill. Right? So in this case, the first pressure distribution diagram, that pressure distribution diagram is due to the surcharge weight. The surcharge weight is uniformly acting over the whole load. Right? So the pressure distribution diagram, the first pressure distribution diagram is a rectangular distribution diagram where the rectangular distribution diagram is due to the surcharge and the intensity is Q into Ka. So what is Ka again? Ka is 1 minus sin pi upon 1 plus sin pi, and it is found to be 0.33. Then the first distribution diagram is to the surcharge. Then there is another distribution diagram. That distribution is due to the self-weight of the soil and which is again a triangular distribution, right? So here the intensity is Ka into gamma into H. Ka into gamma into H. So what is Q? Q is 24 multiplied by 0.33 and it is found to be so here we will just consider this is the area. So it will be 24 into 0.33 and This is the first distribution diagram that is due to the here. This is A2, which will be acting at h by 3 distance from the bottom, and here you can just calculate. This is A1, which will be acting at how much distance? It will be h by 2 distance from the bottom. As it is a rectangular diagram, so it will be the CG of rectangle will be at h by 2 distance from the bottom, and here there is a triangle. Therefore, it will be at h by 3 distance from the bottom. So, what is the total height of the wall? It is 6 meter. So, this h by 2 is found to be 3 meters, and here it will be Z2 is found to be h by 3 distance, means it is 2 meters, right? So here you will just calculate the total PDA is equal to A1 plus A2. So what is A1? A1 is equal to, as the distribution is a rectangular distribution, so what is the area of rectangle? It will be this multiplied by height. So it is 24 into 0.33 into h is 6 meter. And what is A2? A2 is half of 0.33 into 18 into 6 into 6. So total PA is found to be 172 kilonewton per meter square. And this will be acting at a distance of Z bar is equal to PA1 into Z1 plus PA2 into Z2 divided by total P. Right? So here this is found to be 2.37 distance. Right? So this is by this way, when the problems are given for the sandy soil, it may be asked like this. Right? In this case, we will be now discuss. This is for the particularly for cohesion-less soil, right? Now, if the soil is a cohesive soil, then naturally some changes we have to made into this, and we will just see the derivation for that soil, right? So I think this idea has been covered or clear for all. When there is a simple soil, when there is a dry cohesion-less soil, the diagram is a triangular distribution where 0 at the top, maximum at the bottom. When it containing surcharge at its top, then the distribution is a rectangular one. When in between there is a water table or the layered side with backfill is there, in that case we have to independently calculate the pressure and in the individual layer. Suppose this is the first layer, there is a dry cohesion-less backfill, and on the bottom layer we have to consider a first layer is considered to be the surcharge, which is acting uniformly over the interface of first and second layer. Is it clear to all? Now we will discuss the clayey soil. So when the soil is a clayey soil, the distribution is somewhat different. Clayey soil. Or when there is a cohesive soil. Now just remember that cohesive soil can be stand unsupported up to certain depth. Means when we make the excavation into the soil, suppose we want to make the excavation, one there is a sandy soil, another there is a cohesive soil or black cotton soil. So once we try to make the excavation into the sandy soil, we have to provide immediate support, because sandy soil cannot stand unsupported without any support. Therefore, the pressure is immediately acting from the top itself, right? And it will be increases with the depth because the sulfate is increasing. But when we are making the soil, making the pit into the cohesive soil. Suppose this is the cohesive soil, and we just want to make the pit into the cohesive soil. So these cohesive soils can be stand unsupported up to certain depth, but after certain depth, it starts caving. It starts caving. Means what is meant by caving? Caving is the falling of the sides of the excavation. If suppose this is the unsupported one, so after certain depth, it may be after 2 meter or 3 meter, we have to provide once the excavation increases than 2 meter. It may be more than 2 meter. In that case, we have to that may false, right? That may false, and therefore we have to provide them a support in the form of sheeting and dressing. So this is the excavation. So how this depth is being decided? How this depth is being decided? So this depth is considered as ZC. Sorry, this where the depth of potential crack is an important criteria. One more thing, suppose this is the black cotton soil, and in the summer season when water is getting evaporated from the soil, there may be a formation of cracks. There may be a formation of cracks, and these cracks are called as shrinkage cracks, or it is called as depth of potential crack, or it is also called as tension cracks, or it is also called as tension cracks. So these are the cohesive soils. When these cohesive soils are exposed into the atmosphere into the summer season, due to the moisture movement, some moisture getting evaporated from these portion, and these type of shrinkage cracks may be formed. Generally, these cracks are of depth of 1 to 1.5 meter depth. It may be extended up to 1 to 1.5 meter depth and extended for 5 centimeter to 10 centimeter wide. So this depth is an important parameter in such type of numericals, and this depth is called as ZC. This depth is called as ZC. It is also called as depth of the tension cracks, right? So as per the field point of view, the soil can stand unsupported without means soil need not to provide any support, and that depth is called as critical depth. So here we can see this is HC. This is HC. What is HC then? HC is depth of unsupported depth or unsupported This is depth of unsupported or unsupported length of excavation. Unsupported length of excavation means we need not to provide any support up to this depth. Means up to HC, or it is also called as HC is a critical depth. It is also called as critical depth, and this HC is equal to twice ZC. Means if suppose the depth of potential crack is suppose 1.5 meter, so if such type of soil we want to make the excavation, so up to 3 meter depth we don't have to provide any support, and after 3 meter when the excavation reaches more than 3 meter, in that case we have to provide a support in the form of sheeting and bracing. So these two depths are an important parameters in solving the numericals for a clay soil. Then, as I said, these will not exert its pressure on the wall, right? Up to this depth, it will not exert any pressure on the wall. It can be stand unsupported, right? So that depth is ZC, and here we have to provide a support. When the excavation reaches to HC, after that we have to provide a lateral support, because actually from that depth the soil exerting the pressure over the wall, right? So in this case we will now see the derivation for the cohesive soil. Derivation for cohesive soil, right? So again, what we will assume here, we will again consider a retaining wall. This retaining wall is H is equal to some depth of the retaining wall H. Then this soil is backfill. This backfill is having cohesion. There may be a friction. or the density. So these are the properties of the backfill material. Now here we will assume any point at certain distance z. So here we will just assume this is any distance z from the top, and here the distance is assumed as, or the point is assumed as p. So as we know, some pressures, any mass below the ground level is considered as P. So naturally there will be two pressures which is acting over it, and that pressures are vertical pressure, that is sigma V, and the another one is sigma H. So what is sigma V? Sigma V we have already discussed. It will be gamma into Z. That is the sulfate of the soil which is placed above this point. And here, this sigma H will be considered as P. That is the active work pressure. So as it is active work pressure, and we are considering pushing the wall towards back, pushing the backfill like this. So as there is a movement of the wall, the pressure, that is PA, is getting released, and therefore sigma 1 is considered as, sigma B is considered as major, which is equal to sigma 1, and PA is considered as minor, and that is sigma 3. Right? Now we will just assume the condition of plastic equilibrium. So here, this is the condition of plastic equilibrium. Therefore, what is the equation of plastic equilibrium? It is sigma 1 is equal to sigma 3 tan square alpha plus 2c tan of alpha. So this is the equation. Sigma 1 is equal to sigma 3 tan square alpha plus 2c tan alpha. Now what is sigma 1? Sigma 1 is the major principal stress, sigma 3 is the minor principal stress, C is cohesion, and what is alpha? Alpha is equal to 45 plus 5 by 2, and that is the angle made by the failure plane. Suppose this is the specimen, this is considered as a soil specimen, and here we will just apply any load on it. We will just apply the load up to its failure. So the failure is taken place from where it will be taken place. The failure is taken place through a weaker plane, and in this type of soil, when there is a clay soil, the failure plane or the weaker plane is like this. In this case, this is suppose the failure plane. Then this will be alpha. Alpha is the angle made by the failure plane, and here this alpha is equal to 45 plus 5 by 2. Right? Alpha is equal to 45 plus 5 by 2. So here that alpha we will take into consideration. Now in this case, what is sigma B? Sigma B is sigma 1, and sigma 1 is equal to gamma into Z. So it will be gamma into Z, then equal to PA, it will be tan square alpha plus 2c tan of alpha. So in this case, we are interested to find out the value of PA. So it will be gamma into Z minus 2c cot of alpha is equal to PA tan square alpha. So in this case, again we will just take this tan square alpha in the bottom. So it will be gamma into Z cot square alpha minus 2c cot of alpha, which is equal to PA. As we will take this tan square in the bottom, so it will be gamma into Z upon tan square, means it will be gamma into Z cot square alpha minus 2c cot alpha upon tan alpha, so it will be 2c tan alpha. So again 2c tan alpha divided by tan square alpha, so tan will be cancelled, and again it will be 1 by tan is a cot alpha, right? So here gamma into Z cot square alpha minus 2c cot alpha, this is P. Now here at the top of the wall, PA Z is equal to 0. At the top of the wall, z is equal to 0, and if z is equal to 0, so in that case this will be cancelled or this will be 0, and therefore PA and z is equal to 0, it will be minus 2c cot of alpha. PA at z is equal to 0, it will be means at the top. Now at the top pressure is negative, because I earlier said that the pressure in the cohesive soil will be acting at ZC distance after ZC distance, right? So here it will be a negative pressure at the top. Then at the bottom of ball, what is Z? Z is equal to H, and therefore PA, where Z is equal to H, it will be gamma into H cot square alpha minus 2c cot of alpha. So the pressure, again, no doubt, the pressure at the bottom in this case also, the pressure at the bottom will be maximum, the negative pressure at the top and pressure will be maximum at the bottom. Here there is a negative pressure as there is a minus 2c cot alpha, and positive pressure at the bottom. Now tell me, if there is a negative pressure over here and positive pressure over here, so somewhere the pressure will be 0, at somewhere the pressure will be 0, and that depth is called as depth of ZC, that is the depth of potential. Right? Now just we'll switch over to the next part where the pressure is 0. Now, see here, in this case, we will again draw a diagram. In this case, this is the distance which is 2c cot square alpha. It is minus 2c cot alpha, and at the bottom it will be gamma into h cot square alpha minus 2c cot of alpha. Right? So in this case, this is pressure. The distribution diagram is like this. It will be a negative positive distribution, and this distance at which PA is 0. This distance at which PA is 0, and this distance is then called as ZC. So how you will get the ZC now? At distance ZC, PA is equal to 0. So we will just equate the previous equation with 0, and therefore what is PA? It will be gamma into Z. Cot square alpha minus 2c cot of alpha. So this is the equation for PA. Now in this case, this PA will assume as 0, right? So it will be gamma into H into cot square alpha minus is equal to 2c cot of alpha. Now here we will just cancel these cot square and cot square alpha. So what is the value of ZC then? ZC is equal to gamma into H. It will be 2c upon gamma into tan alpha. So it will be ZC is equal to 2c upon gamma into tan alpha. We'll just take the values. Here ZC, we just interested to find out the value of ZC. Just take ZC over here, 2c upon gamma. Cot square will be cancelled, and here cot will be cancelled. So 1 by cot is again tan alpha. So ZC is equal to 2c upon gamma into tan alpha. So here this D is 0, at which the depth is ZC. Now Where this HC is calculated now, what is HC? HC is equal to twice ZC. And therefore, HC is equal to 4C upon gamma into tan of alpha. So this is the equation. Now, which pressure we are taking into consideration as an active pressure? So here, positive pressure distribution diagram will consider for the active earth pressure. So this is negative and this is positive. So here, this portion of the soil, we will just assume it as a PA. So here, what is this distance then? This distance is H minus ZC. H minus ZC. Therefore, total PA is act as total pressure, active earth pressure is area of positive pressure distribution diagram. Area of positive pressure distribution diagram, and here that is PA is equal to half of gamma into H cot square alpha minus 2C alpha. Gamma into H cot square alpha minus 2C cot of alpha. What is the height of this triangle? The height of the triangle is H minus Z. So it will be H minus Z. So this is the area of the positive pressure distribution diagram. Half of this distance multiplied by the height of the triangle is H minus Z. And again here it will be at Z is equal to distance H minus ZC by 3 is the distance at which the pressure is at. So this is the basic difference between the pressure pressure for the cohesive soils. Now I think this is being clear to all, and in the next class we will see the numericals based on it, right?